this whole thing is 0. Which means that the volume underneath that thing is 0? What?
It would never exist in the first place.
So before I show you this, let me ask you this. If we go back to Cal 1 and we were to look at the sine function, and I were to say find the area between 0 and 2 pi, what would the area be? It would be 0, right? But that's because it counts area above the x-axis as positive, and it counts area below the x-axis as negative, right? So even though we're getting a volume of 0 here, it doesn't necessarily mean that this thing is like flat. So here's the picture of it. So here's our domain, right? That's our domain. Our x is between 1 and 2. Our x is between 1 and 2. Our y's are between 0 and pi. We have a surface. Now check out this surface. Okay, so this surface is doing some weird stuff, right?
Okay.
And then we have, let's plug in, and I hope you can see from where you are that some of that surface is above the xy plane and some of it is below. I think it'll be better when I put the solid in here. So let me put the solid in here and let me take the surface out. And so you can see that there's some volume above and some volume below. Right? And so here, if I wanted to know, hey, look, what's the area of one arc of this sine function, I would just integrate from 0 to pi instead, and I would get that, right? So I'd actually have to know these x-intercepts so I could, restrict it, right? Here, if I wanted to know the volume of just this shape right here, this part above, I would need to figure out what that is. Right there, where it intersects the xy plane. In other words, if I look at it from the top like this, I would have to adjust my domain so that my domain is no longer a rectangle. My domain would have to be here, down, and like this. And that's no longer a rectangle, is it? And that's the next section, is what happens when we want to integrate over things that aren't rectangles. But that's the next section. It's not right now. Okay, so here is the actual theorem, okay? Fubini's theorem says that so long as your function is continuous, so as long as your surface doesn't have any crazy things happening, asymptotes, holes, as long as we're continuous on the entire rectangular domain, this has to be a rectangle for this theorem. As long as you're on a rectangular domain, the order of integration does not matter. So this is me formally saying you don't need to worry about it, all right? That's what allowed us to do that last problem and reverse the order. No, we won't do that. Okay. Yeah, let's do this one because this is, don't know if I gave us, yeah, okay. So this is a very special case, all right? Not of Fubini's theorem, just of doing double integrals. This is a very special case. Let's say that your surface that you're trying to do the double integral on happens to be the product of two functions where one of them is a function of x and the other one is a function of y. This is the only time ever that you can split the double integral into two single integrals and multiply the answers. You're never allowed to do this in general. Like what I'm saying is this, like back in calculus, if you're at Cal 2, if you're asked to integrate that, right? You have the student that does this, right? Back in Cal 2, and they're not here, right? They're not in this, they didn't make it to Cal 3. You can't take a product in an integrand and split it into two integrals. You can't. Cal 2 would be simple if that were the case, right? So this is no go. Well, here there's a special case where you can take a double integral and split it into two single integrals, but this piece in here has to be two functions separated by multiplication, each of them independent of one another. So let me show you this example. So take a look at this one. See our surface? Sine x times cosine y. This is a function of x only, this is a function of y only, and they're separated by multiplication, right? So if I want to do this, what I can do is I can set up my double integral. Doesn't matter which order I go. I'm going to go dy dx like this, which means my outer limit is 0 to pi over 2, and my inner limit is the one on y. Oh, it's also pi over 2. Okay, so according to this theorem, this special case, I am allowed to split this into two. I can go integral from 0 to pi over 2 of sine x dx times integral from 0 to pi over 2 of cosine y dy. This is valid. All right? That's valid. So we just do that, figure out what that is, do that, figure out what that is, multiply the answers, we're done. That'll come up later because we'll be doing problems and all of a sudden we'll see things like this and I'll take it from here to this, and I just, got to make sure you're following why I'm allowed to do that. Okay, some properties of double integrals. These are things that pretty much follow from Cal 2. So things work the way you think they would. If you have two functions being added or subtracted in a double integral, you can split that into two double integrals and add or subtract them. If you have a constant in a double integral, the constant can come out of the double integral. If your function f, your surface, is always above another surface, then the volume under the top surface should be more than or equal to the volume of the surface below it, right? So does that seem pretty reasonable? Is that it? Okay. Now, what about in Cal 2, when you first start out, you're saying, here's F, find the area, right? And then as you progress, you say, okay, here's F, here's G, find the area between them, right? And to do that, all you did was you figured out which one was on top, which one was on bottom, and you subtracted the two. That's exactly what this is saying. If we are trying to find the volume between two surfaces, then what we'll do is we will do the double integral over the rectangle of the top surface minus the bottom surface, which we can do either all together in one, or we can split them up into two. So the picture of this looks like this. Can you all see that? Yeah. We have like an upper surface, a lower surface, the domain on the ground, and we're trying to find the volume between that. So that's like the three-dimensional version of this picture. I don't know why it's there twice. Oh, is that it? Yeah, that's it. How do y'all feel?
Like just
Great, ready to go? Ready to keep grinding?
As a person, or just how I feel about this?
Well, we're supposed to do one more section today, and I'm weary. I can go, I can keep going, but yeah, we need to. We don't want to fall too far behind.
I mean, are we falling behind an hour?
No, we're on pace if I can get this next section in. I think if we can do just the first half, I'll be happy. So this is the point at which in a normal semester, not summer, you would go home and you would practice those problems from 12.1, and then you'd come and we'd start 12.2. So 12.2, now what we're doing is we're changing the fact that our region on the ground doesn't have to be a rectangle anymore. So when it comes to this, these regions on the ground can be very challenging. So what we do is we first start trying to categorize them. So we've already looked at this type of region where it was AB cross CD. This is our rectangle. X is between A and B, Y is between C and D. That's the easy way. Yes?
I have a question.
Yes, good.
How would you determine which surface is on top and the other one?
That is a great question. The question is, how do you determine which surface is on top and which surface is on bottom? That's going to be actually pretty tough. Most of the problems that we will see, it'll be obvious from the functions themselves, like for example this. F of xy equals, let's say, 4 minus x squared minus y squared versus g of xy equals x squared plus y squared. So something like this. So for this, what you can kind of see, hopefully, is that this one, the biggest value this can be is 4. And then this is going to be, like, if you take y out, that's a parabola opening down. Take x out, it's a parabola opening down. So you've got this paraboloid like this. And this one's the opposite. It's going up. So on at least where they intersect one another, this one would be on top and this one would be on bottom. But in general, it's not easy because you basically have to set these equal to one another, right? So let's say you're given a rectangle and you're given a plane, right? And I need to look at the homework. Let me look at the homework. I don't think you're ever really going to have to go after that too much because it is challenging. It is hard to figure out which is on top and bottom sometimes. Let me see what these. You can test 1 point, and that's what would be happening right there. But in a different part of the region, it might be something else. Like that one I showed you with that sine one. Like on one part it was above, but the other part is below. So let me see here for 12.1. Just make sure you're not going to run into that problem. So here, yeah, in the homework, they're not going to, you're not going to be asked to find the volume between two surfaces, okay? If they do, they'll tell you like this. They'll say, find the volume of the solid under this elliptic paraboloid and above this other one. So there in the wording, they're kind of telling you that on this region, this one, the one's on top and the other one's on bottom. Yeah, but generally it's hard to do that. Was that the only question? Does that answer your question? Okay. Yeah. All right, I'll leave it alone. I could keep going too much on that. All right, so this is what we did in the previous section. Now we're going to try and look at a different type of region that's not a rectangle. So the first one is what we call a type 1 region. And don't worry, there's only 15 types. So, no, I'm kidding. There's 2 types that we talk about in here, okay? So there's one type. First type is, instead of being a rectangle, calling it R, we're going to call it D. So it's going to be more like the domain. It's all points X and Y such that your X is stuck between 2 constants. That looks familiar, right? X is between 2 constants. But now, your y is not between 2 constants, it's between 2 functions of x. So look at the picture. So that should look a lot like in Cal 2, like the area between 2 functions, right? You have like a top function, a bottom function, and then you have your x's are between a and b. So if our region on the ground, the domain, looks like this, it's called type 1. All right? Let me give you a simple example of this. That's a type 1 region. Because your x's are between what? 0 to 2, right? So your x is allowed to float between here and here, and then your y values are constantly stuck between these 2 things. What are they stuck between? This function of x right here, which is up there would be called g2 of x, That's the function x, right? And then what's the bottom function? This is your top function. And then what's your bottom function here? That right there, which is just the constant 0 function, or y equals 0. Yes? So x between two constants, y between two functions of x. Another example. That's type 1 region. Because your x's are between what? Oh, I forgot to put what your y's were between here. Y was between 0 and x, right? X between 0 and 2, y is between 0 and x. Here, your x's are between 0 and 1. And then your y's are always stuck between 0 and 1 minus x squared. Does that help a little bit to see it that way? How about this one? Is that a type 1? So are your x's stuck between two constants? Are your x's always between these two constants? Yes. Now, what are the constants? You would have to figure out where these hit each other, right? Which could be done, but I think it's obvious it's 1 and negative 1. So your x's here are between negative 1 and 1. And your y's here are between, so your y's always have to be between two functions of x. The top function is which one? So, or let's say the smaller one is the x squared minus 1, right? That's your bottom function, and then your top function is the 1 minus x squared. That would be a type 1 region. X between constant, y between two functions of x. We're going to do some practice with these, so hopefully you'll see them. They'll become a little more clear as we do a couple of examples. So what does the double integral look like then? Well, here's how things change. If you'd like to find the volume underneath this surface down to the xy plane, you're going to do the double integral over d this time, not r, because it's not a rectangle. D, the domain of the surface with respect to area. But now look at this. Look at how this changed. Your outer integral has to be x. You don't have the choice anymore of flipping it. So because x is between two constants, it's the outer integral. The inner integral has to be with respect to y, and look at what the limits of integration are. It's the actual functions of x. Now, in addition to this, if you have two surfaces and you want the volume between them, so this is what you were just alluding to, you have one on top, one on bottom, then everything's going to run the same way, right? The only thing that's different is that when you look at this top surface and bottom surface, you're trying to find the volume between them. The only thing that's different now is the shadow on the ground is no longer a box, okay? No longer a square or rectangle. It's now a type 1 region on the ground, okay? So when your shadow is a type 1 region on the ground, then you set up that integral. You just subtract the two. It's the same thing. But the order of integration is actually important now. Let's do this one. Let's call it a day. Find the volume under z equals x plus 2y. That is a plane, right? On the region bounded by y equals 2x squared and y equals 1 plus x squared. where should we start with this? Maybe draw the domain, right? Let's draw the domain. So D, I'm going to draw it in two-dimensional space, is going to be y equals 2x squared. I'll draw that. Let's do that in blue. And I'll draw the other one in red. Okay, so the blue one, 2x squared, is a parabola that opens up. I know that because I'm a Cal 3 student, and I should know that, right? And then the other one is 1 plus x squared, which is another parabola that opens up but is moved up 1. And it's wider, right? It's wider because having a 2 out here makes it more narrow. So this other one should start here and be wider, which means I should intersect that other one somewhere. Now, of course, a graphing calculator would help here, but these are pretty elementary functions, so I think you could get them. Do you see the region? You see this region? Now, is this a type 1 region? So are your x's, so I'm going to go to where they hit each other. Are these x's always between, so if you're somewhere in here, are your x's between two constants? Yes. Are your y's stuck between two functions of x? Yes, as long as you're in there, you're stuck between those two, right? All right. This is a very bad drawing because it's supposed to be symmetric. Like this point should be up here, so let's start with trying to find our restrictions on x. How are we going to do that? How do we figure out where the x's, how the x's are restricted here?
Put them equal to each other.
Yeah, they're the intersection of those two curves. So we have to figure out the intersection of those two curves. So we set them equal to each other. I didn't label these. I'll label them. This was y equals 2x. And then the other one was, no, I just got that backwards. This one was y equals 2x squared. I even said it wrong. And this one is 1 plus x squared. So we're going to find their intersection points by setting them equal to one another. So intersection, I set 1 plus x squared equal to 2x squared, and well, that's going to work out real nice, right? It's just 1 and negative 1. So that's the x coordinate where they hit one another. So I know this is 1, I know this is negative 1. Probably could have just done that visually, just plug in 1 here and 1 there, but algebraically that's what we did. So negative 1 to 1. And then the y values are bounded between the two functions. So which one goes down here on this side of the inequality?
2x squared.
2x squared, right? Because this is the bottom, and then the top is the 1 plus x squared. There we go. So that's our domain. Now, what is the surface we're trying to find the volume underneath? Like, what is the actual surface? It's this right here, right? Which we need to look at as a function of x and y. We need it to be f of x, y. That means we need to solve it for z, but it's already solved for z. So our double integral is going to look like this. What are the limits of integration on the outer integral? Negative 1 to 1. The inner integral. So I'm going to put y equals 2x. You don't have to put y, okay? Y equals 2x. Y equals 1 plus x squared, right? That's the second time I've done it. 2x squared. And then the integrand, the thing that's being integrated, is x plus 2y. That's our surface, our plane equation solved for z. And then it's d what, d what? dy dx. You have no control over that. If it's a type 1 region, you've got to go in that order. All right, let's continue. Negative 1 to 1. Okay. We have to do the antiderivative of this with respect to y. So that one, xy, and then the next one, y squared plus y squared, and we're evaluating that from y equals 2x squared up to y equals 1 plus x squared. And then after we're done with all that, we'll go dx.
And you plug, in order to solve that, you plug them in.
You plug them in for x. I mean, sorry, for y. Sorry. You plug those in for y. So yeah, it's going to suck, but, you know, such is life. All right, so now we go in here and we say, let's see, this goes first, right? So here into here for y, so we get x times 1 plus x squared, and then plus that thing squared. Okay, so that's what I get when I plug in 1 plus x squared for y here and here. And then minus, and now we've got to plug in 2x squared here and here. So x times 2x squared plus 2x squared squared, so 4x to the fourth. And all of that dx. And I'm going to stop here because you're all Cal 3 students. So I'm going to stop here because at this point, this is just polynomial stuff. Distribute, expand, distribute negative, polynomials, power rule, antiderivative, collect like terms, power rule, plug in 1 and negative 1 should be pretty straightforward. So just as a kind of a heads up of where we're going with this, on the final exam, it's going to be really unreasonable for me to ask you to take integrals all the way down to numerical answers. So a lot of the problems on the final are going to be set up but do not evaluate the integral because just time. So it's just about, you know, can you set it up? Now these problems are a little bit on the basic side still because we have very simple functions and simple regions, but the idea is going to be, can you get me to this? You know, can you get me here? If you can get me here, then yeah, we have different ways of doing that. But have a good 4th of July. Stay out of trouble. Oh, test. Yeah, you want those back. Sorry about that. So remember, we said a week from today, next Wednesday, if you want those 11.7 points, you've got to make 2 corrections, right? 2 problems, fix them up, do them on separate paper, okay? And then if you want an additional 5 points,